Dear students, welcome to this lecture on digital logic and system design. Today we are going to see the design of an accumulator. On the previous turn we had seen a processor which is based on ALU and shifter, and it had the register files. Today we are going to see a processor design using an accumulator. As we have seen earlier, that accumulator is a special purpose register which besides storing data can do lot many other things as well, right? So this will be the processor unit with an accumulator. So this is our accumulator, which we will denote by register A. A stands for accumulator usually, and then there will be some combinational circuit which we are going to design shortly with having the control variables. So one of the implied inputs will be from the accumulator itself. Then there will be another input coming from some other source. This may be register files, this may be the external world or whatever. This combinational circuit, after working on that A and B, will store the result back into register A. So in that sense, register A will be implied as one of the data providers and will also be implicitly the result storage register, right? So this is the register that we have to design today. These are the micro operations that we expect an accumulator to to execute. Under control variable P1, we want that B should be added with the contents of accumulator and stored back into accumulator for the addition operation. The accumulator gets cleared, the contents of the accumulator get complemented. The contents of A are ANDed with the data provided at B terminal and stored back into A terminal. So over here, all of these places you see that the result goes back into the accumulator. So that is the special status that accumulator enjoys. Similarly, A operates for logical OR operation on the data provided by B and stores it back into A. This is exclusive OR A and B. This is shift right A. This is shift left A, and this is incrementation of the contents of the accumulator, right? So they have the control variables. When this control variable is raised, this should be done. When this is raised, clear should be done. When P3 is raised, complementation. When P4 is done, then ANDing. When P5 is done, then ORing. P6 exclusive OR. P7 shift right. P8 shift left. P9 incrementation. And over here you see this doesn't require a control variable because this is something that should be done, regardless of the control variable, which control variable is there and which is not there. Whenever the contents of the accumulator become 0, then some 0 flag should be set, right? So this is what this should be done regardless and independent of the control variable. So that is why no control variable is mentioned. For example, if on the contrary we had mentioned a control variable P10 here, so that would have meant that it is only when P10 is high that you have to check if A is equal to 0, then Z is equal to 1, which is not the case. We do not want to raise a control variable to let us know whether the contents of accumulator have gone 0 or not. It should be independent. That is why it should be independent of the control variable. That is why we are not putting any control variable here. The presence of a control variable or the absence of the control variable, regardless of that, the 0 flag should be set whenever the contents of the accumulator go 0. So these are the micro operations for an accumulator. How do we get it? First, let us consider add B to A. So this is a register. Obviously, this will be a synchronous device. Now this is the present state. These are the inputs, and this is the carry in, right? So when this is 0 plus 0 plus 0, it should be 0 with a carry 0. With 0 plus 0 plus 1, there should be the next state should be 1 because it has to get stored in the accumulator back. So this is the previous state of the accumulator and this is the next state. I told you in the beginning that implicitly one of the operands come from the accumulator and the result goes back to accumulator, right? So 0 plus 0 plus 1, there should be a sum 1 and a carry 0. 0 plus 1 plus 0, this should be, the sum should be 1 and a carry 0. 0 plus 1 plus 1. the sum should be 0 and the carry should go 1, right? 1 plus 0 plus 0, a sum 0 and a carry 1, carry 0. 1 plus 0 plus 1 will be the sum 0 and a carry 1. 1 plus 0 will be giving us the sum 0 and a carry 1. And 1 plus 1 plus 1 will give me the next state of the accumulator, which is the sum as 1 and the carry Ci plus 1 as also 1, right? So I can have the flip-flop inputs 0 to 0 from present state to next state using the excitation table of the flip-flop. 0 to 0 will be 0 dash or 0 cross, whatever. 0 to 1 is 1 cross, 0 to 1 is 1 cross, 0 to 0 is 0 cross, 1 to 1 is cross 0, 1 to 0 is cross 1, 1 to 0 is cross 1, 1 to 1 is cross 0, right? So I can have now the K map as we do in the design of a sequential circuit, synchronous sequential circuit. Now for JAI, let me populate the 3 variable K map. It is 0 1 1 0, so 0 1 1 0, and all of these I don't care. So the reduced value is JAI is equal to BICI dash plus BI dash CI. There will be these two will be combined and these two will be combined, so I'll get this expression. KAI, cross 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 cross, then 0 1 1 0. So correspondingly you see the same expression will result, BICI dash plus BI dash CI, even though the inputs were different, but the combination will give me the same result. Now Ci plus 1 is 0 0 0 1, so 0 0 0 1 and 0 1 1 1, right? So I can get it as Ci plus 1, AI plus AIBI plus AICI plus BICI. There will be 3 combinations like this, this and this, right? So let me show you. Yeah, so over here this will be the combination. They will combine like this and they will combine like this. Over here the combination goes like this, the combination goes like this, right? And in this case there will be a combination like this and another combination. Let me change the color. Another combination like this, and then yet another combination, maybe some other color, this color, another combination like this. So this will be the corresponding this will be the corresponding expression. Now I can say that this should happen when the control variable is P1. So I can write JAI is equal to BICI dash P1, so that whenever P1 is high, then only this should be applied. Similarly BI dash CI P1, the same control variable, and now KAI will have the same expression, so that is why combining with P1 also it will have the same expression. Ci plus 1 is AIBI plus AICI plus BICI. It won't have the control variable P1, right? These are the required inputs and this is the output, right? So input will be the control variable. Control variable will not be there at the output. Ci plus 1 is the output coming from the accumulator, right? So that is why it doesn't have the control variable P1. So that is how you will be able to realize the first micro operation in the accumulator. Now clearing P2, what should be there? We all know that since we are designing the accumulator using a JK flip-flop, right, the ith stage using the JK flip-flop, clearing happens when JAI is equal to 0 and KAI is equal to 1, right? That is when the JK flip-flop gets cleared. So that is what it does. JAI is equal to 0 and KI is equal to P2, because clearing is done using P2, right? So whenever P2 is high, then KAI will be 1 and JAI will be 0, then it will get reset. For complementation, we know that both of them have to be 1 1, so that it toggles. If it is 0, it gets to 1. If it is 1, it gets to 0. So that is why JAI is equal to P3 and KAI is equal to P3 as well. So that whenever P3 is high, I'll get 1 1 at both the terminals. And if P3 is 0, I'll get 0 0. So no change, right? No change over here. Similarly here, if P2 is 0, then there will be no change, 0 0. It is only when P2 is high that it will get reset to 0. It will get cleared. And this will get into the toggle mode, complement. Now AND P4. You see, so we've covered these three. Right? Now let us go to ANDing. For ANDing, we know that it is bitwise ANDing, and so there is no concept of carry in or carry out, right? So if this is the present state and the input comes this, then I'll have the next state as the AND of these two. So it will be 0, 0, 0, 1. It will be 1 only when both of them are 1, 1, right? Correspondingly, the required flip-flop inputs as it happens in the design of a sequential circuit will be 0 to 0, 0 cross, 0 to 0, 0 cross, 1 to 0 cross 1, 1 to 1 cross 0. So JAI will have 0, 0 cross 0. So I can assume that both of them are 0, so JAI will be 0. Because it helps me, these don't care conditions, they help me when I am substituting them as 0, so that everything is 0. Right? They were 0 anyway, so by treating them as 0, I'll be able to get the entire thing as 0. Now KAI will combine these two, right? So this was BI, so this will be BI bar. So it will combine to give me, it will combine like this, so as to give me KAI is equal to BI bar, right? So that will be about the ANDing which will happen. So basically JAI will remain 0 and KAI will be BI dash P4. P4 dot 0 will be 0 anyway, so we will not bring in P4 here, we will bring in P4 here. KAI will be BI dash P4, so that whenever P4 is high, ANDing takes place between AI, the ith stage of the accumulator, the ith bit of the accumulator, and the ith bit of the operand B. Likewise, OR when it happens with P5, so 0, 0, 0, 0, 1, all these three will be 1 in the OR gate, and so required flip-flop input 0 to 0, 0 cross, 0 to 1 is 1 cross, 1 to 1 is cross 0, 1 to 1 is cross 0, coming from the excitation table of the JK flip-flop. So you design the, you put the K-map. So you notice that the K-map for ANDing, ORing, exclusive OR is just a 2 variable K-map, whereas the K-map for ANDing was a 3 variable K-map, because there the CI was involved as well. And also we had to have a K-map for CI plus 1. So 3 K-map of 3 variables each. But in any logical operation like AND or 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 exclusive OR, there is no carry in, no carry out. So only 2 K-maps and those two of 2 variables each. Right? So this is populating the, so this is populating the K-map corresponding to JAI, which is 0, 1 cross cross, 0, 1 cross cross. So these two will combine and I'll get JAI is equal to BI, right? Whereas here it is better to keep KAI is equal to 0. I can treat them as 0. Both of them I can treat them as 0, right? So KAI will be 0. So effectively it will be JAI is equal to BI P5 and KAI will remain 0. Now coming to exclusive OR, it has to be 0, 1, 1, 0. Present state, next state, excitation table of JK flip-flop, 0 to 0, 0 cross, 0 to 1 is 1 cross, 1 to 1 is cross 0, 1 to 0 is cross 1, right? So now I can populate the 2 K-maps of 2 variables each, 0, 1 cross cross, so 0, 1 cross cross, then cross cross, 0, 1 cross cross, 0, 1. Over here they will combine like this, they will combine like this. So they in fact will be the same, BI, BI. So since it has to come with the control variable P6, so it will be P6 BI. Similarly, it will be P6 BI, right? So that was about exclusive OR. Now what remains? Let me go back. See, okay, up till this point I've covered up till this point. Seen addition, how to clear, complement, and or exclusive OR. Shift right and shift left, they are interesting too. Shift right. JAI will be AI plus 1 P7, right? JAI, suppose this is ith bit, and we have to do the shifting write. So it should receive data from I plus 1. It should receive data from I plus 1. So the data should come from here and it should go here like this, right? That is what shift right would be, and shift left would be just the opposite. So what is happening? JAI is AI plus 1 P7 and AI plus 1 dash P7, so that it behaves as a D type flip-flop. It behaves as a D type. Okay, so what will happen? That JAI will be AI plus 1 P7, while AI dash plus 1 P7 will go to KAI. So this will essentially, this JK flip-flop will become a D flip-flop, because whatever you are giving at JAI, the complement of it is coming at AI dash plus 1, AI plus 1 dash, right? So it will essentially behave as a D type flip-flop. Now shifting left P8, the same thing, the similar thing will happen, but with AI minus 1, because suppose this is I minus 1, suppose this is AI minus 1, so the data has to come from here in shifting left and it has to go to I, right? So whatever is stored here, that will go to the jth terminal, and the complement of it will go to the kth terminal of the ith stage. Okay, so if suppose you have a 0 here, so 0 will come to J and 1 will come to K, so it will get reset. That means 0 has shifted to I, from I minus 1 to I, which is like shift left. Suppose a 1 was here, so J will receive 1 and K of ith stage will receive 0, so it will get set, it will become 1. So 1 from I minus 1 has moved to I, so this has shifted left. So for shift right, shift left, you can have these design equations, right? This one, and the for shifting right, this one, right? So that covers again, see, so these two are also covered this way. Now incrementation. In order to understand incrementation, let us consider this circuit, 3-bit synchronous binary counter. We have studied it already. 3-bit synchronous binary counter we have studied. See what happens. We are giving, if E1 is equal to 0, you know, P9 is the control variable for incrementation. Suppose I don't want to increment, so I am putting P9 is equal to 0. When this is 0, this entire line gets 0. This entire line is 0, because they are AND gates. So since they are feeding both JK terminals of all the flip-flops, so there will be no change in the contents of all the flip-flops, right? Now it is when E1 is equal to P9 and P9 goes 1, now this is 1, right? So if this is 1, this stage will toggle at every incoming clock pulse, right? Whereas this one will toggle only when P9 is 1 as well as A1 is 1, right? So that is how it happens, you know, from 0 0 0 0 0 1 0 1 0, right? And then 0 1 1. So this stage is toggling everywhere, 1 0 0 1 0 1 1 1 0, and finally 1 1 1. So you see this stage, this is A1, this is A1, this is A2, and this is A3. So this is toggling at every incoming clock pulse because P9 is 1, right? Now this toggles only when this is 1, right? See, when this is 1, it toggles from 0 to 1. When this is 1, it toggles from 1 to 0. When this is 1, it toggles from 0 to 1, and so on. After that, it will again be 0 0, right? So this toggles at every incoming pulse. This toggles when there is an incoming pulse as well as the previous stage is 1, right? Now over here, this one, you see, this will toggle only when this P9 is 1, A1 is 1, as well as A2 is 1. So you see, it was 0, so it will remain 0 and will toggle only when both of them, A1, A2, both of them are 1. Again it will toggle, the next stage would be 0 0 0, and the cycle will repeat. Cycle will repeat from here, it will go back to this place, right? So you see it toggles again when both of them are 1. So this is the 3-bit synchronous binary counter. We have discussed in detail already. It is just that I'm revising it quickly today. So what I can say that JAI is equal to EI, KAI is equal to EI, where I am naming them as E1, E2, E3. This is the eth terminal of all the flip-flops. So talking about the ith stage, suppose the ith stage is the third stage. So JAI is equal to EI and KAI is also EI. And what is EI? EI plus 1 is EIAI, right? EIAI. You see everywhere this is E2. For instance, E2 is E1A1 and E3 is E2A2, right? So for I is equal to 1 to n, I can design AI plus 1 is equal to EIAI. And E1 should be P9. This is the only initial condition. E1 should be P9. So this is how I get the design equations for the incrementation, right? So I have done all of them. This is also done now. If A is equal to 0, then Z is equal to 1 is simple. Yeah, check for 0. Check for 0 is simple, because when what I can do, check for 0 means check for all ones at Q dash terminal of all of them. So Q dash and Q dash. So basically I am checking A1 dash and A2 dash and A3 dash, right? So that is what I am writing. Zi plus 1 is equal to Ziai dash. Z2 is A1 dash Z1 dash, or Z3 is Z2 dash Z2 A2 dash, right? Z2 was Z1 A1 dash, right? Z3 is Z2 A2 dash, right? If this is A2, this will be A2 dash, right? And similarly Z3 will be, let me go back to the laser pointer, and Z3 will be Z2 and A2 dash. So I can write Zi plus 1 is equal to Ziai dash for I is equal to 1 to n. Z1 should be 1, because if you make this 0, then the entire line will be 0 regardless of what the values of A1 dash, A2 dash, A3 dash are. So this should permanently be 1 for checking. Suppose there is a case where you don't want to check it, then in that case you keep it 0, right? Then you make it 0. But since we want this to be checked regardless of the control variable, so I am keeping this permanently as 1, right? So Zn plus 1 will be Z. The final Z will be Zn plus 1. Variable Z becomes 1 if the output signal from the last stage is 1. So whatever be the last stage, this I have taken 3. So Z4 is the last stage. If I'll take 4, then Z5 will be the last stage. If I am taking n such stages or n bits in the accumulator, then n plus 1th value of Z will be the final flag Z, right? So now one stage of accumulator can be designed this way. Combining all the input functions for the J and K inputs of flip-flop AI produces a composite set of input Boolean functions for a typical stage. JAI, P1 was addition. We had PI CI dash. Plus this is BI dash CI P1, right? Plus P3. Plus, BI P5, right? And this is BI P6. Over here P2 is missing because it doesn't take part in clearing, whereas this takes part in clearing. So P2 is here. P3 will be at both these places because this is corresponding to complementation. This is corresponding to complementation, right? And then again you see this is B4 was corresponding to ORing. B5 was corresponding to just let me check. Yeah, from here, yes, P4 was corresponding ANDing. P4 was corresponding to ANDing, P5 to ORing, and P6 to exclusive OR. Okay. So this will be this is corresponding to addition. These two corresponding to addition, and this is corresponding to complementation. This is corresponding to ANDing. This is corresponding to ANDing. This is corresponding to ORing, exclusive OR. Where it is missing, that means it should have been, it must have been 0 there, right? And this is about shifting, right? This is about shifting, and this was shifting left, shifting right, and then finally the incrementation, EI, right? So each stage in the accumulator must also generate the carries for the next stage. So this is another design equation. CI plus 1 will be AI BI, as we had obtained in the case of addition. EI plus 1 is EI AI, as we had obtained in the case of incrementation, and ZI plus 1 is ZI AI dash, as we had obtained in the case of zero checking, right? So these are the design equations, JAI, KAI, the ith stage of the accumulator. One stage means the ith stage of the accumulator will have these design equations. Just realizing them in the form of a logical function, one stage of accumulator I can get here. It essentially contains these design equations only, right? So these are the design equations that are embedded into the into this logic circuit, and this is the ith stage containing this. All is the combinational part. This all is the combinational part, right? This is the ith stage or ith bit of the accumulator, right? Remember the very first diagram that I had given, this one. See, combinational circuit is here, and this is register A of n bits. So one bit of register A, the ith bit of the register, what is the combination circuit corresponding to that? What is the combination circuit corresponding to I plus 1th bit, and so on, right? So this is the ith stage of the accumulator. And then using this, I can have n bit accumulator. For example, if you are getting 4-bit accumulator, then it should have input carry, it should have serial input for shifting left, it should have P9 for incrementation, right? It should have Z1 as 1, permanently 1 for checking 0. It should receive B1 over here, the data coming from the external world. Should also receive A2 for shifting right. And what it should give me, it should give me Z2, the 0th checking for the next stage, carry for the next stage, carry out of this stage will be the carry in for this stage, and then A1, going to this place in order to do shifting left, right? And E2 for incrementation purpose should pass on here. Likewise, so it receives B2, Z2, C2, A2, E2, A3, right? And A3 will be this one for shifting right. And then correspondingly Z3, C3, A2, E3 will be generated. 4 outputs will be generated. These are the 4 outputs, 1, 2, 3, 4, right? These are the 4 outputs that should come out of it, right? Let me see. Yeah, okay. So 4 outputs, Z3, C3, A2, E3. Okay, Z3 and the, yeah, okay, fine. So from this stage it will go to this stage then, right? So inside you will have the entire circuit. This entire circuit will be inside this block. Okay, so you must be wondering why am I not giving JAI and KAI? That is because they are inside, and JAI, KAI are being generated using B4, Z4, C4, A3, E4, A5, right? They are being generated, as well as it is accepting P1 to P8, these control terminals. It is accepting clock pulse, and this is giving me the serial input for shifting right. This will be the final output carry. This will be the increment carry if you want to add more stages, and this will be the Z. If you want to add more stages, this Z will be fed to the next stage. Otherwise, this will be the final 0 flag, right? So this is the accumulator based processor design, as we have gone through the design of this accumulator. So this is a special purpose register. Let me go back to this one. So this is a special purpose register in that sense. It accepts it accepts control variables. And based on that, it operates with the current contents of register A and the current contents of B for the next contents of register A, which may be the addition of A and B, which may be just clearing A, which may be complementing A, which may be ANDing of A and B, which may be ORing of A and B, which may be exclusive OR of A and B, which may be shifting left of A contents, shifting right of A contents, or just incrementing register A, the entire table over here, right? So we will stop here for today. Thank you very much for your patient listening, and this completes the accumulator based processor design. And how do we design the ith stage, and how do we replicate it as many times as the number of bits in the accumulator. Okay, thank you.